Chapter 5. Structures, Practices, and Construction Techniques. To put your hands in a river is to feel the cords that bind the earth together. Barry Lopez. Introduction. The goal of this chapter is to describe the tools developed so far that achieve induced meandering objectives. Deflectors, grade control structures, and vegetative treatments have applications that modify either lateral or vertical dimensions of a channel. The main tools of induced meandering are deflectors and grade control structures, vegetation manipulation, and bank destabilization. Deflectors, such as baffles and vanes, are used to influence lateral dimensions and the plan form of the reach, while weirs exert vertical control, modifying slope and bed features. Grade control structures, such as rock weirs, rock channel liners, and filtered dams, are used to hold the bed at the desired grade or modestly steepen the grade in order to mobilize available sediment and erode a meander apex. Other structures used to control bank erosion and the grade include cross veins and constructed step pools, such as a Zuni bowl, rock bowl. Lateral control. Deflectors include picket and boulder baffles, tree-length log baffles, picket and post vanes, and vegetation. Deflectors function by either increasing or decreasing lateral erosion of stream banks at critical points, as called for by the project design. Deflectors are used not only to protect banks and promote sediment deposition on point bars and floodplains, but also to initiate erosion of the opposite bank. Baffles. A baffle is a deflector, a structure used to create lateral erosion of a stream bank in order to widen the channel and alter the meander geometry of the treated reach. A baffle functions by concentrating flow and increasing stream velocity along the opposite bank while decreasing velocity along the adjacent bank. The result is accelerated erosion of the opposite bank with a commensurate increase in sediment deposition along the adjacent bank, causing point bar formation. Photo 5-1. As the resulting point bar becomes colonized by riparian vegetation, it becomes increasingly resistant to erosion and more effective at deflecting flow toward the opposite bank. In order to achieve the desired meander pattern, baffles must be properly sized and spaced. In 1997, Zeedyk first used baffles to initiate or induce meandering in an artificially straightened reach of Pueblo, Colorado wash at Hubble Trading Post National Historic Site, Ganado, Arizona. Various shapes, sizes, and materials were tested in the design and construction of the baffle prototypes. Experimental shapes included arrowhead, spoon, and wedge shapes. The most effective shape was found to be that of a 30 to 60 degree right triangle. Other shapes were less effective at deflecting flow or were more subject to scour during flood events. Referring to Figure 5-1 above, the triangular baffle is configured so that the short leg A protrudes outward from the bank toward mid-channel width. The long leg, B, forms the base of the structure parallel with the bank length, and the hypotenuse, C, forms the face of the structure, which serves to deflect or wedge flow toward the opposite bank. To emulate the vertical dimensions of a point bar, the upper surface of a baffle must taper downward from the edge of the stream bank to mid-channel. At the bank, the top of the baffle should be level with bankful stage D, and the tip should be no higher than 1/3 maximum bankful channel depth. Having the correct surface profile and height is vital to the proper performance of a baffle if it is to initiate point bar development. The key feature is that floods having depths greater than bankful flow smoothly over the surface of the baffle with minimal turbulence. A taller baffle will act as a groin and create an eddy pool downstream from the structure as the flow swirls past, washing away sediments and preventing point bar formation. Entrained sediments must be able to wash across the baffle at velocities less than the deflected flow for deposition to occur. The geomorphic role of the baffle, when applied to incised channels, is to initiate erosion of the opposite bank and point bar development, leading to meander formation, channel widening, and channel lengthening. Sequestration of sediments occur as stratified bank deposits form a new floodplain. Having successfully initiated meander formation, assuming that the structures are properly sized, spaced, and situated, the role of the baffle gradually diminishes until it is ultimately encapsulated by newly deposited sediments and flourishing plant growth. The baffle gradually disappears from view. The ecological role of the baffle is to provide a substrate for colonizing vegetation, food, and cover for animal life. Pools with undercut banks, which form opposite the baffle, provide hiding and escape cover for fish, frogs, and invertebrates. Perennial or intermittent pools may develop where none existed before. Sediments deposited on evolving point bars provide seed beds for colonizing riparian vegetation such as sedges, rushes, willows, and cottonwoods. As vegetation density increases, overflow velocities decrease, allowing for the deposition of fine textured particles such as silt, clays, and organics that build fertile topsoils to support more vegetation. Stands of short-stemmed grasses and spike rushes, for example, are favorite habitats for spiders, which in turn attract young wild turkeys, waterfowl, and shorebirds. Various materials can be employed in baffle construction. Those most commonly used include rocks and boulders or wooden posts and pickets. Photo 5-2. Locally, the choice of material will depend on availability, the nature of bed and bank deposits, and expected stream velocities. For example, cobbles and boulders that may be readily available and close at hand in cobble-bedded channels would be the logical choice. However, one should be careful not to disturb archaeological sites on the banks or terraces. Pickets and posts, on the other hand, are seldom suitable for use in cobble channels, even when readily available, because of the difficulty in installing them by hand. Cobbles and boulders are normally less available in sand, silt, and clay-bedded channels and are difficult to stabilize if used, but posts and pickets can be easily driven into fine-grained substrates and, if driven deeply enough, resist shear more efficiently than boulders. Cobbles and boulders function well when simply placed on the channel bed in tightly packed arrangements. This is particularly true where the baffle is situated on the inside bank of an established or evolving meander bend and is, in effect, sheltered from high-velocity flow. Structures built of blocky or angular boulders resist shear stress more effectively than rounder pieces. Where boulder baffles are installed in deeply incised reaches and subject to high stress, baffles should be installed with footers or with 1/2 of their height buried beneath the bed surface. Obviously, larger pieces should be used in steeper channels with higher velocity flows and increased shear forces. Since the purpose of a baffle is to accelerate erosion of the opposite bank, objects such as roots or rocks that might resist erosion should be removed from the outside bank in order to expose bank materials to erosion. Baffles may be used in various applications to achieve specific objectives. For example, locating 2 or more baffles on the same side of the channel to increase the radius of an existing meander. Another example is extending a baffle with its sloping surface the full width of channel in order to function simultaneously as both a deflector and weir. The latter application is useful when treating small channels with low stream power and cohesive banks where it is important to focus maximum erosive force against the bank. Baffles should be sized and shaped according to the channel type, Figure 5-2. An oversized baffle is likely to catch logs and woody debris during high water events and block laminar flow, postponing the evolution of a point bar. The main consequence of making a baffle too tall is scour on the downstream side. If too wide, there is the risk of the tip washing away during a flood. If too low or too narrow, there will be no channel response. If too short, relative to channel length and the angle too abrupt, widening will not occur, and shear stress on the structure will increase, causing the structure to be washed away. Rock and boulder baffle. In addition to meeting basic geometric requirements regarding shape, width, length, and height, many other considerations must go into the construction of a boulder baffle to assure proper function and durability. Figure 5-3, page 90. The first consideration relates to sizing of rocks. Rocks used in the construction of a baffle must be large enough to resist expected flood forces. Beyond that, the rocks need to be uniformly sized and proportioned so that the surface of the completed baffle is streamlined. Photo 5-3. Any large or outsized rocks protruding above or outward from the surface of the baffle will generate turbulence and retard point bar formation. If rocks are unevenly sized, a depression should be made to accommodate the large ones. Smaller ones can be tucked in between their larger neighbors and/or rotated so that the long axis is vertical, making them of equal height. To increase resistance to shear stress, boulders can be placed in trenches dug into the stream bed so that at least half of the boulder is buried beneath the bed's surface. This treatment is especially useful along the A and C dimensions of the baffle, but seldom necessary along the B dimension. Digging footers is laborious for handmade structures, but if a machine is used, installing baffles with dug footers is highly recommended. Flat rocks can be placed on their edge, narrow sides, and packed tightly together to increase their resistance to shear stress. This technique is called book stacking. Where baffles are installed on the inside bend of an existing meander, shear stress will lower, reducing the necessity of preparing footers. Boulder baffles installed on sand, silt, or clay can be cradled in geotextile fabric to help bind the structure. However, the use of textiles will impede establishment and growth of vegetation. Often, it is quicker, easier, and less expensive to purchase and deliver the needed rock than to collect it on site. In other cases, rock of the correct size may be locally abundant and free for the taking. Care is needed when gathering rock from the project site. Sometimes, rock can be gathered from the gully bottom and banks without damaging the system. In fact, removing rock from the opposite bank will speed up the channel forming processes. By the same token, removing rock from the stream bed adjacent to the structure will retard development of the point bar. When utilizing rock material from an on-site location, depending on land ownership and funding source, it may be necessary to have an archaeological survey of the quarry sites and travel routes to assure compliance with legal requirements. Picket baffle. Picket baffles are relatively easy to install by hand in clay, sand, and gravel-bedded streams. But as bed materials become larger, driving pickets by hand becomes increasingly difficult. Photo 5-4. Helpful hints to speed up the process include opening a pilot hole by using a digging bar, using a small steel cap placed over the end of the picket to prevent splitting when struck repeatedly by the hammer, or trimming pickets split by hammering to create a new flat surface for striking with the hammer. Usually, posts are driven until they will go no further and then cut at the proper height for that position in the baffle. Photo 5-4. To ensure that pickets are driven deep enough, it is helpful to pre-mark the picket for that depth. Digging a starter channel will initiate bank erosion. Photo 5-5. For more information on pickets, refer to Appendix E, page 199. Picket and rock baffle. A variation on the picket baffle is the picket and rock baffle, in which the spaces between the pickets are filled with rocks. Figure 5-5, page 90. Rocks of various size can be used to fill the voids because the pickets will tend to secure the rocks in place. No rocks should protrude above the plane of the baffle surface. Photo 5-3. In ephemeral gullies having large seasonal flows, the picket lines in a picket baffle can be woven with small flexible branches to increase roughness and enhance sediment deposition. Photo 5-6. In perennial channels, the picket lines of a baffle function better without woven materials. The picket lines need to be left open to allow accumulation and sorting of sediment by size class during successive floods. Picket baffles and perennial channels should be monitored after major events, and any captured debris that protrudes above the surface of the baffle should be removed. Large debris could generate turbulence and prevent deposition on the point bar. If channeling on the bank side of a baffle is noticed during the monitoring process, rocks or pickets can be added between the bank and the baffle to expand the floodplain and accelerate point bar development. If this channel is not stopped, a cutoff channel will reduce the force expended against the opposite bank while eroding the near bank. If all is going well, baffles can be extended as the opposite bank recedes to meet geomorphic goals. Photo 5-7, Figure 5-3, Figure 5-4, page 90. Whole tree baffle. Steve Reichart of the Tierra y Monte Soil and Water Conservation District, Las Vegas, New Mexico, has pioneered the use of whole trees as baffles for the restoration of deeply incised ephemeral gullies in the Sapeo Creek watershed, San Miguel County, New Mexico. After first calculating the appropriate meander length to determine baffle spacing, baffle locations were identified and staked. Chapter 7. Two 30-foot-long, pole-sized ponderosa pine trees with most of the limbs attached were used to construct each baffle. Photo 5-8, page 91. Any limbs that would prevent the tree from lying flat on the bed were cut flush with the trunk and woven into the other limbs. The trees ranged from 6 to 9 inches in diameter at the butt ends. The trees were placed side by side, parallel to the channel, with their butt ends upstream. The tree along the bank was placed with the butt about 10 feet downstream of the other tree. A cedar post was driven into the stream bed midway between the trees and toward the upstream end to hold the trees in place and prevent them from being washed against the bank. Both logs were wired to the same post. The next baffle was placed on the opposite bank at the proper spacing. During the first flood event, large quantities of sediment were caught and deposited among the tree branches, quickly creating point bars and a new floodplain approximately 1 foot above Thalweg elevation. A meandering channel was formed between the log structures. Vegetation soon colonized the bars. Cattle that were grazing the surrounding area trailed along the meandering channel, accentuating the meander pattern and facilitating further erosion of the exposed banks. It would be relatively easy to extend the baffles by adding a third tree-length log to each structure, thereby forcing further erosion of the opposite bank and expanding each point bar. Once deposition occurs in and around the branches of the trees, it is highly unlikely that subsequent floods would dislodge them. No weirs were used in this application of the induced meandering method. Approximately 1/2 mile of channel was treated using tree-length log baffles. There are many ways to be creative in starting a meander. For example, nicking the opposite bank to expose mineral soil or digging a starter channel will hasten erosion of the bank. Planting sedge plugs or willows along the margins of the structure and between the rocks or pickets will help to build a network of roots that bind the structure together. The new sedge plants will increase the surface roughness and capture fine textured soil particles from the water column. Material estimation. Practitioners new to baffle construction usually underestimate the amount of material needed to construct a baffle. Figure 5-6. This information is needed not only as a guide to procuring sufficient material to build the structure, but also to estimate the amount of fill to be placed in the channel when applying for Clean Water Act permits, such as Federal 404 and State 401. Chapter 7. Vanes. A vane is a type of deflector. It is an upstream pointing barb used primarily to divert high-velocity flow away from a cut bank or the outboard side of a meander bed. This will reduce erosion, prevent scrolling, and maintain the proper meander radius. Figure 5-7. Vanes can be constructed of boulders, logs, or vertical wooden posts. The vane functions by moving the zone of maximum velocity outward from the bank. A second use of the vane, when applied in the practice of induced meandering, is to direct flow into the opposite bank, initiating bank erosion and causing the channel to widen in that direction. Photo 5-9. This is similar to the manner in which a baffle functions. As the channel widens opposite the vein, it begins to deposit sediment along the bank adjacent to the vein where velocities decrease, thereby maintaining the channel width, figure 5-8. As a result, a bend begins to develop, which may in turn evolve into a new meander. Several considerations govern the design and installation of the vein. First, the angle of incidence of the vein with the bank should be 20 degrees or less. Slightly less is better. Photo 5-10, figure 5-10, page 94. A vein with a wide angle of incidence is more apt to fail than one with a narrow angle. Second, the angle of descent, declination, from the bank at the bankful elevation to the tip of the vein at the bed of the channel should be in the range of 2 degrees to 7 degrees. A vein with a steep angle of descent is more apt to fail than a shallow one. Third, the structural components must be adequate to withstand high shear stress, especially when placed in deeply incised channels with fast-moving currents and cohesive banks that resist erosion. Figure 5-9. It is important that the bank end of the vein does not extend above planned bankful level. Veins can be built using a variety of materials. Most commonly, veins are constructed with posts, but boulder and logs also work well. Heavy equipment, such as a backhoe, is needed to excavate trenches for logs and pits for boulders, and to maneuver heavy logs and boulders into place. Proper placement of logs, boulders, and footer rocks is critical to structure performance. Post-vein. Because many restoration projects are initiated by individuals or groups having access to manual labor, volunteers, family, friends, but without the funding or desire to hire machinery, a feasible alternative to the use of machine-built structures was needed. Finding an alternative to mechanized equipment led to the development of the post vein, which can be built by hand. The post vein is constructed by driving posts vertically down into the stream bottom to depth significantly deeper than the scour depth, normally 3 to 5 feet, marking the posts to the correct height to achieve the proper angle of descent from stream bank, and then trimming the excess. Having first perfected the technique by building modest-sized post veins manually, it was an easy step up to install larger post veins in larger rivers by machine. Post veins were developed and first used by Bill Zeedyke for installation by hand labor at Hubbell Trading Post National Historic Site on Pueblo, Colorado Wash in June 1998. Their purpose was to withstand the high shear stress occurring within a deep, narrow channel contained by cohesive clay banks that resist erosion. Boulders were more easily displaced than posts by flood flows. Morphologically, a post vein functions similarly to a boulder or log vein, the main difference being that a portion of the flow squeezes between the posts rather than spilling over the surface of the structure. Because flows are moving more slowly through the vein than in the open channel, sediments drop out and point bar formation begins in the lee of the structure. Ecologically, veins facilitate the establishment of stream bank vegetation by providing optimum seed bed conditions and sheltering newly established plants from flood forces until they can become well rooted. As plants' height and root densities increase, stream bank soils become well stabilized and the plants begin to protect the veins which initially sheltered them. Veins may also provide resting cover near select foraging areas where fish can hide in nooks and crannies between the posts and boulders while lurking in wait for passing prey. Caution should be observed when extending a post vein beyond mid-channel, because the erosive power of the bankful discharge increases rapidly as a larger proportion of the total flow is temporarily detained behind the vein, which can cause the vein to fail. A post vein is a straight-edged structure protruding from the stream bank into the oncoming current at an angle from the stream bank not exceeding 20 degrees, though less is better. The top edge of the vein dips downward at an angle from horizontal, beginning at bankful level at the stream bank and ending at bed elevation at mid-channel. Figure 5-9, page 94. For post veins, straight, sturdy wooden posts 4 to 7 inches in diameter at the fat end and 4 to 6 feet long are recommended for most applications. Using a sledgehammer, posts are driven into the stream bed to a depth of 3 to 5 feet, depending on cohesiveness of bed materials. Opening a pilot hole with a digging bar or auger may facilitate installation. 6-inch posts should be spaced on 18-inch centers, leaving a space of about 12 inches between posts. Thinner posts should be spaced closer together. After all posts have been driven to the correct depth, the posts are marked for cutting. The bank end post is marked at bankful elevation and the tip end post is marked just above bed elevation. A string is stretched between these marks as a guide to marking all the other posts at the proper angle of descent. Photo 5-11, page 95. The string must be checked with a line level to make sure the angle does not ascend, which could lead to structural failure. Cut off excess post lengths with a saw and remove them from the job site. Optimally, the apex of the angle between the vein and the bank can be partially filled with rocks. Photo 5-12, page 95. The rocks should be too large to slip between the posts. The rocks should not be piled higher than half the height of the vein edge because doing so promotes turbulence and scour. To install a vein at the proper angle to the bank, place a marker on the bank at the planned apex of the meander. Measure out to mid-channel and make a second mark there for the tip of the vein. This measurement is the width of the vein, A. Multiply the width by 3 and take this measure from the apex to a point on the bank downstream, which will be the length of the vein, B. This procedure will produce an 18-degree right triangle. Figure 5-10, 5-11. When the opposite bank begins to recede in response to treatment, the vein can be extended into the channel to chase the opposite bank. A point bar will evolve downstream from the vein on the same side. If the vein is too tall or filled too high with rock, turbulence will prevent formation of a point bar. Post-vein installation with machinery. Post veins can be installed with the aid of a backhoe or excavator. Where the riverbed is comprised of cobble or boulder-sized material, it may be too difficult to pound posts into the bed by hand, and mechanized equipment can make the job easier. When working on ephemeral channels, the trenching method is more efficient than hand driving. It may also be possible to bore holes using a tractor-mounted auger. Photo 5-13. Holes can be dug manually with a post hole digger and bar. Finally, where large diameter posts are used and stream beds are soft sand, gravel, or muck, it may be possible to grasp the post mechanically in the jaws of an excavator and simply push the post into the stream bed. Photo 5-14. On the Rio Puerco, a sand-bedded channel having a bankful width of 56 feet, posts were pushed into the stream bed to appropriate depth and cut to height using a chainsaw. These posts averaged 12 inches in diameter and 12 feet long and were placed on 30-inch centers. Vanes averaged 45 feet along the hypotenuse with 19 posts per vane. Photo 5-15. Machine-built post vanes were first installed by Van Clothier in 2005 on a creek in the Burro Mountains. To install a machine-built post vane, dig a trench about 6 feet deep. Photo 5-16. Begin digging at the downstream or bank end of the vane, storing the excavated material in a pile nearby, but not on existing vegetation. When the trench is long enough, place posts butt end down in the trench, leaning them upright on the streamward edge of the trench. Place dead men, horizontal logs pinned with boulders, along the bottom of the trench to prevent the posts from tilting during flood events. When the trench posts are all carefully set in place, fill in the trench and put any additional material on the bank side of the vane and compact it in place. Photo 5-17. To compact the soil, roll it with the wheel of the backhoe. Once the backhoe has moved to the next site, snap a chalk line and cut the posts off at the proper design height and angle of descent. Photo 5-18. It is desirable, especially if significant scour is expected, to backstop the posts with horizontal deadmen. Depending on cohesiveness of channel substrates, the walls of the trench may collapse soon after digging. It may be necessary to work quickly to install the posts before the walls collapse. In that case, work in segments so that posts are set as the digging progresses. Place each bucket of excavated material in the trench alongside the posts, and continue adding posts as the trench progresses so that the trench is filled with posts and dirt as fast as it is being dug. Boulder vane. A boulder vane should be built with rock footers placed in trenches beneath the structure. Trenches should be dug below scour depth and at least 2 times the height of the above-ground boulders. For a boulder vane to survive a flood in sand-bed streams, trench depth must be at least 4 times structure height. The proper technique is to place the footer rocks first and then install the surface rocks, beginning at the bank and working toward the tip. A cutoff sill is recommended to prevent overbank flows from going around the structure. Figure 5-12. Log vane. Log vanes can be used to protect banks or create meanders and generate point bars. Proper installation of log vanes is much more technical than post vanes. A trench is dug into the bank wide enough to accommodate the log. Photo 5-19. To ensure that the log can withstand expected shear forces, approximately 60% should be in the bank. Photo 5-20. The log should be placed with the butt in the bank and pinned down near the bank with a boulder. A footer log can be placed slightly upstream and under the vein log to plug the gap and prevent undercutting.
The angle where the log intersects the bank can be filled with rocks or a live willow clump to help stabilize the structure, but nothing should protrude above the log. The rocks will initiate development of a bankful bench. It is recommended that a geotextile fabric be placed in the upstream triangular area between the log and the bank before this area is backfilled. The filter fabric is nailed along the inside top quarter of the log with washer-capped nails and then stretched over the toe of the bank. Place and trim the fabric so that it is not visible. The fabric will prevent water from scouring beneath the log. Manipulation of vegetation.
The purpose of induced meandering is to speed channel evolution by promoting erosion or deposition as needed to achieve design objectives.
Selective planting or removal of protective stream bank vegetation can increase or decrease the rate of erosion or deposition. For example, if a segment of exposed stream bank is protected with vegetation while the opposite bank remains unprotected, the channel will tend to move toward the exposed bank and bend in the direction of the vegetated bank. Planting one bank with willow cuttings but not the other can achieve this objective. The channel will shift toward the unprotected bank. Figure 5-13. Overzealous willow or tree planting to protect the banks of an incised channel against erosion will retard channel evolution and actually delay formation of an accessible flood plain. Figure 5-14. Throughout many portions of the Southwest, stream banks are heavily armored by dense stands of invasive plant species, such as tamarisk and Russian olive. Many volunteer organizations are enthusiastically cutting, pulling, piling, burning, and chipping the invaders only to replant the disturbed areas with dense stands of native species, keeping the channel locked into a Roskin G or F type. Scarring a stream bank opposite a natural or artificial deflector can be used to accelerate bank erosion and encourage meander development. Bare soils erode more readily than soils protected by the roots of trees, shrubs, sedges, and grasses. Removing protective plant cover to expose the stream bank helps the river do the work of channel shaping at a more rapid pace. Ideally, the plants are simply transplanted to the opposite bank.
Willow planting protocol. Identify local source of healthy willows. Gather willow cuttings on the same day as planting. Use as many species of willow as stock location has to offer in order to match species requirements with soil characteristics at planting site. Stem size is determined by the size of hand clippers. Optimal size of cuttings is 3 feet long by 1/2 inch in diameter. Cuttings are trimmed at an angle to make a sharp point for planting and to distinguish root end from stem end. Strip all leaves and stems from the cuttings in order to reduce moisture demand, but consider that the willow cuttings have no roots. the cuttings will grow new leaves and roots in proper balance. Willow stems are kept wet before planting by placing them immediately in the stream or a bucket of water as soon as possible after cutting and trimming. If transporting, place in a bucket of water with about 4 inches of water in the bottom or wrap in wet cloth such as burlap. Any more water only makes the bucket too heavy to carry. Plunge a hole with a digging bar and firmly push the cutting down to the water table. Bottom of stem must intercept the permanent water table. Plant cuttings in clumps of 3 to 4 stems per hole, utilizing 2 or more species of willows per clump. Top of the hole should enter the bank at bank full level. Soak hole with river water and then tamp soil to remove air pockets from hole. Trim cuttings about 1 to 2 feet above soil level. If trimmings are long enough, plant them too. Coyote willow cuttings prefer gravelly soils. Other species may prefer heavier soils. Tolerance to prolonged inundation varies among species. This protocol was developed by Bill Zeedyke and the Quivira Coalition for the Rio Grande Cutthroat Trout Habitat Restoration Project on Comanche Creek, Valle Vidal, Carson National Forest, New Mexico. www.comanchecreek.org. Photo 5-21, volunteers prepare willows for planting along Comanche Creek, Carson National Forest, Taos County, New Mexico. Vertical control. Just as deflectors are used to control the plan form of a stream reach, various types of structures are used to control the slope of the reach. Structures used to control the slope or grade of a stream are broadly termed weirs. Weirs take on many specialized shapes, sizes, and characteristics depending on their purpose and structural components. Beside weirs, other structures used to control grade or prevent bed erosion include channel liners, constructed step pools or cascades, and even especially adapted road crossings such as hardened fords and culvert placements. Check dams are a form of grade control, often used in ephemeral gullies. These are not used in induced meandering. See page 11.
Weirs. A weir, when used in induced meandering and properly located and sized relative to planned channel dimensions, slope, and meander pattern, may be considered temporary in nature. Over time, the stream will replace it by a riffle-run sequence. Weirs determine bed, elevation, and slope. Where the plan is to establish a Rosgen C channel, weirs are placed midway between the tips of the baffles as measured at the upstream edge of the weir. Weirs should be as wide as the bankful width of the channel and no taller than 1/3 the bankful depth of the planned channel, not necessarily the existing channel. Figure 5-15. Since stream power increases with increasing velocity, maintaining a minimal drop at weirs minimizes shear stress and scour depth. The increase in shear stress is relatively insignificant if the height of the drop is kept to 1/3 or less of bankful depth of the channel. Weirs should flare upward at either end to blend with bankful level. In concept, a weir replaces the run in the typical riffle, run, pool, glide sequence.
If the weir is properly located, shaped, and sized, the stream will build a new riffle upstream from the crest of the weir. In order to establish a constant channel slope, weirs are designed and built with a predetermined drop in elevation from one to the next. For example, to maintain a 1% channel slope, if two successive weirs were 100 feet apart, the top of the second weir would be 1 foot lower than the first or pour over. Figure 5-16. Stream flow accelerates as water pours over the weir. This will scour sediment from the bed and banks of the next downstream meander bend apex. Velocity can be increased within limits by the height of a given weir. The consequence of increasing the height will be to increase the risk of undercutting the weir. It might also cause aggradation at the next upstream pool. The ability to increase velocity can be a useful tool when attempting to undercut a cohesive bank in order to widen the channel. In the typical induced meandering application, weirs are seldom installed perpendicular to direction of flow, but rather at a slight angle to flow line. Photo 5-22. The angle is called skew. The purpose of the skew is to direct flow around the next downstream deflector in anticipation of the evolving meander pattern. Aligning the weir with the existing channel rather than the design channel would retard meander development. Project planning and design procedures are described in Chapter 7. When a structure is staked, dimensions of the structure are noted on the stake, including length as measured parallel with the channel, width and height above Thalweg, and direction of skew, if any. The outline of the structure is marked on the ground with a surveyor's paint, paying special attention to planned bankful elevation along the left and right edges of the structure. As construction proceeds, elevation can be monitored with a leveling instrument such as a laser level. Because riffles and runs are three-dimensional, weirs, which emulate a natural riffle-run complex, should be built in 3 dimensions and not as a dam with a narrow weir edge, such as a check dam. For stability, the length of the weir should be equal to or greater than the width of the bankful channel. Wicker weir. A wicker weir is a low dam across a creek or gully built by driving sharpened stakes or pickets into the channel bed and then weaving flexible branches between the stakes perpendicular to the direction of flow. Photo 5-23, Photo 5-24, page 102. Wicker weirs are well suited for sand and clay channel beds. If built on gravel stream beds, they tend to be abraded by the gravel bed load during flood flows. Wicker weirs are designed to control stream bed elevation, channel slope, and pool depth. Boulder weir. Boulder weirs are suited for gravel and cobble channel beds. They are constructed of several parallel rows of boulders placed on the channel bed at right angles to the planned direction of flow. A row of footer rocks buried beneath the downstream side is necessary to control scour. For greater resistance to shear, it is desirable that all rocks in the weir be placed in a trench half as deep as the height of the boulders. Boulders should be tightly spaced, flaring up to the bankful edge of the channel on either side. Photo 5-25, Figure 5-17. Smaller boulders, 6 to 8 inches in diameter, are suitable for small channels up to 1 foot maximum bankful depth. For channels greater than 1 foot deep, Boulders larger than 1.5 feet should be used to withstand the higher shear stress. When working in a stream bed with abundant boulder-sized rocks, choose boulders larger than 90% of their neighbors. D90. One-rock dam. A one-rock dam is a variation of the boulder weir and is most suited for streams and gullies less than 15 feet in width. Figure 5-17, photos 5-26, 5-27, 5-28, and 5-29. One-rock dams are so called because they are only one rock deep, but they are several rows long. Rock size varies depending on depth of the channel, usually about 1/3 the depth of the bank full channel. Rocks should be carefully matched in size to create a uniform, relatively smooth surface from the upstream to downstream edge. Smaller rocks can be used to chink the gaps between larger rocks, but rocks should never be placed atop one another in order to gain the desired height. If they are, the upper layer would be swept away during a flood. In the case of an ephemeral channel, once the one-rock dam has been installed, the first flow event, whether of flood magnitude or smaller, will deposit fine bedload particles, organic debris, animal manure, plant propagules, and seeds in the spaces between the rocks. As the interstices fill, plant materials will germinate or sprout, tightening the spaces between the rocks. The manure and organic debris will furnish nutrients and conserve moisture, while the rocks act as a mulch, sheltering the new plants from heat and trampling. As the new plants grow, the tapestry of roots will begin to bind the rocks in place.
Eventually, with rigorous plant growth and subsequent flood events, the structure will heal over and become very stable.
If there is any scour below the structure, this should be repaired by adding another row of rocks on the downstream end to fill the scour hole. If there is any scour below the structure, this should be repaired by adding another row of rocks on the downstream end to fill in the scour hole. If the one-rock dam has become fully stabilized, which can take a few months to a few years depending on the sediment supply and precipitation pattern, it may then be desirable to raise the structure by one tier or level of new rocks. Figure 5-18. In less incised channels, just one layer may be sufficient to raise the grade and reconnect the stream with its floodplain. The preferred technique for raising the level of the structure is to add 5 or more new rows of rock, placing the downstream row on top of the first structure about midway between the upstream and downstream edges. The result will be that about 3 new rows will be perched on top of the first structure, and 2 or 3 rows will be placed on depositive sediments upstream of the original dam. Water pouring over the lip of the added tier will fall onto the lower tier without scouring the bed, because these rocks are now bound in place by the network of plant roots. If the upper tier of rocks is placed directly over the original layer without the upstream offset, the height of the drop doubles and accelerated scour would tend to undercut and wash away the entire structure, old and new layers alike. Following the disastrous Cerro Grande fire near Los Alamos, New Mexico in 2000, thousands of one-rock dams were installed on Santa Clara Pueblo lands to treat newly formed gully complexes. After 1 year, all structures were modified by adding a second layer of rocks. Further incision of the gully network was controlled. With the Oso Complex fire of 1997, where many gullies formed over a wide area, rock-grade control structures were not installed. At present, the gullies are still deepening and widening. Tree-length log mat. Tree-length log mats are grade control structures used to stabilize the beds of rapidly advancing gullies in small watersheds by promoting sediment deposition to raise the bed and widen the channel. Tree-length log mats are especially useful in burn areas where dead timber in the appropriate diameter and lengths is readily available next to the gully. Log mats are useful in gullies up to 15 feet wide with watershed areas less than 1 square mile. 4 principles apply to the use of tree-length log mats. 1. Trees should be equal to or longer than 3 times the width of the channel. 2. Trees should be felled or placed parallel with the direction of flow with the top pointing downstream. 3. Trees can be tightly packed together and should only be 1 layer deep. 4. On channel size, rocks can be placed on trunks to secure them in place. Figure 5-19 illustrates the proper placement of logs and expected channel response. The concept is based on the assumption that branches wedge against banks and hold logs in place. Stream bed scour will not occur where water moves slowly between logs because sediment will quickly plug spaces. As sediments accumulate, logs become less and less mobile. Tree-length logs from tall trees are less mobile than short trees or bucked logs. Channel liner. A channel liner is a long, narrow one-rock dam, much longer than it is wide, built in a recently incised gully bottom, and used to armor the bed and or reconnect bankful flow with the recently abandoned floodplain. Photo 5-30. A channel liner is most useful where a new head cut has ripped a tear through a hammock of tightly woven tree roots or through wetland sod. Cross vein. The cross vein, invented by Dr. David Rosgen, 2001, is a grade control structure that decreases near bank shear stress and focuses stream power toward the center of the channel, maintaining a permanent scour pool below the structure. Photos 5-31, 5-32. The structure will establish grade control, reduce bank erosion, create a stable width-depth ratio, maintain channel capacity, sediment transport capacity, and sediment competence. The cross vein is also a stream habitat improvement structure. Rosgen, 2001. In rivers, cross veins are built with boulders, 1 to 2 cubic yards, and are supported by footer rocks installed in the bed to a depth up to 3 times the height of the cross vein above the bed, figure 5-20. Cross veins can be constructed by hand in smaller channels, using the largest boulders that can be moved by hand. Weirs as cascades or step pools. 4 specialized types of weirs are installed to act as energy-dissipating step pools. These include the Zuni bowl or rock bowl, the the rock arc dam, the filter dam, and the log and fabric step falls. These structures are used where the height of the drop is greater than bankful channel depth of the stream. In nature, most streams on steep slopes greater than 4% are classified as a Rosgen A stream type. These streams dissipate energy vertically in step pools rather than laterally via meanders and floodplain access. The water flows over the rim of the step, falls, splashes into a pool, loses momentum, flows gently to the brink of the next rim, and falls again. The process of falling, stopping, flowing, falling, and stopping once more dissipates energy and reduces erosive power by preventing the flow from attaining extreme velocity. Trying to control erosion at a head cut can be a frustrating challenge. The best solution is to mimic how nature solves this problem. Artificially constructed head cut control structures use the principle of the step pool to reduce stream energy and slow the rate of headward erosion. The same principles can be applied to cause a stream to scour out a deep, self-cleaning depression in the channel, which will fill with seepage from the alluvial water table and provide a reliable water source for wildlife, livestock, and people. Zuni Bowl. Bill Zeedyke observed Native American workers on the Zuni Pueblo in New Mexico building head-cut control structures that used the principle of the natural cascade or step pool. Rather than spill water directly over a high falls, the cascade was used to build a series of smaller steps and pools, keeping the velocity within manageable range. There are three key features to a Zuni Bowl: a hardened pour-over, a rock-lined catchment, and a rock-lined backsplash to protect the head wall and sides of the channel. Figure 5-21. The backsplash replicates immovable boulders in a natural step pool stream. To build a Zuni Bowl: 1. Amass a sufficient quantity of boulders and cobble-sized rock on site. 2. Use a shovel, mattock, or digging bar to smooth and widen the surface of the vertical head wall and remove surface irregularities from the scour pool. 3. Build a dam across the channel up to the height of 1/3 to 1/2 the height of the drop and located downstream from the base of the falls, a distance 2 to 3 times the height of the drop. Use the largest rocks for this dam, which will form the lower rim of the bowl. 4. Fill the bottom of the bowl with a layer of rock to armor the bottom. 5. Next, line the face of the backsplash and sides with similar sized rocks, taking the rocks all the way up to the lip of the falls, but not higher. Rocks making up the backsplash should be stacked in an arc like finely crafted dry masonry, using the bottom course of rocks as a footer. Each additional course should be stepped back slightly to lean against the slope for support. During a storm event, water will pour over the lip and fill the bowl to the height of its rim. Photo 5-33. Water falling into pooled water loses energy. The rocks lining the bottom of the bowl protect the stream bed from scour. Moisture retained in the soil under and between the rocks will nurture new plant growth and help to stabilize the structure. Photo 5-34. The result is a simple cascade with 2 drops, each half the height of the original falls. To further flatten the angle of the cascade and lessen the height of each drop, additional pools or bowls might be added. The recommended maximum height per step is 1 1/2 feet. A head cut 3 feet tall would need 2 or 3 steps. One 4 feet tall would need 3 or 4 steps. Finally, to further lessen the drop and to store moisture for plant growth, add a 1 rock dam downstream from the base of the Zuni bowl. Photo 5-35. The upstream edge of the 1 rock dam should be located downstream from the lower edge of the bowl, a distance of 4 to 6 times the total height of the falls. During a storm, water will pool here and further help to dissipate stream energy. Building the structure with geotextile fabric, as shown in Figure 5-21, will help to catch sand and fine gravel to bind the rocks in place, but the fabric will retard plant growth. As a rule, if bed materials are clay, silt, or sand, use the fabric. If gravel and cobble, do not. Rock arc dam with keystone. A rock arc dam can be used as a grade control structure or to create a step falls and scour pool combination that will collect water for wildlife, livestock, or human use. When used in a series, rock arc dams can form cascading step falls that control stream velocity and dissipate energy. A rock arc dam of considerable strength and durability can be built with hand labor by simply applying the principle of the Keystone Bridge. A keystone bridge lying on its side to resist the horizontal force of stream flow. The arc dam requires the presence of 2 large boulders, one on either side of the channel, to serve as opposing abutments like bridge abutments. Photo 5-36, page 108. The arc is constructed by wedging smaller boulders against the abutments and locking them in place with a keystone. The dam arches upstream against the oncoming current and slightly downward toward the channel bed. As a result, the highest velocity flows are concentrated at the mid-channel pour-over. The concentration of flow energy digs a self-cleaning scour hole that will hold water. In a perennial or perennial interrupted channel where the water table is intersected, a permanent pool will result. In an ephemeral or intermittent channel, the pool may not be permanent, but will be the last part of the reach to go dry. To build a rock arc dam. 1. Select a suitable site with opposing abutment rocks equal in height to the depth of the bankful channel or greater. The goal is to place manageable boulders in a shape that arches upstream from the abutment rocks. 2. Amass a supply of rock. If the structure is being constructed by hand, use the largest boulders that can be manipulated with available labor. 3. Start by leaning one of the tallest rocks against one of the abutments. Place another equally tall rock against the opposite abutment. Flattened oblong rocks are preferred. Rocks are placed on edge, with the long dimension parallel with flow and the middle dimension vertical to create the height of the dam. Figure 5-22. The secret to building a structure that will withstand the strongest floods is to wedge each additional rock against its neighbor as tightly as possible by using a rock bar. Continue to work toward the middle using shorter rocks each time until just enough space remains for the keystone rock. 4. The keystone rock should be triangular in shape and wedged into place as tightly as possible so as to force all other rocks outward against the abutments. The narrow end of the keystone should point downstream. It may take some skill and a bit of patience to locate a proper keystone. To be doubly sure of a tight fit, smaller flat rocks can be pounded into any gaps between the larger stones. The finished dam creates a falls where there was none before, and the oncoming flows will serve to force the rocks even more tightly together. Flood flows will deposit bedload upstream of the structure and scour a depression downstream. The depth of the resulting pool can be increased slightly by building a one-rock dam downstream from the lip of the falls, approximately 4 to 6 times the height of the drop. Filter dam. A filter dam is used to raise the bed of a gully by trapping bedload and some washload. Washload is captured by temporarily impounding water and allowing it to seep slowly through the porous structure. The finer bedload particles become trapped in tiny crevices and are retained by plant roots. A filter dam is constructed in 3 zones. The downstream zone consists of 3 to 5 parallel rows of large boulders stacked shoulder to shoulder across the channel. The first row is buried in the bed as a footer. The next rows are stacked against the footer rocks at successively higher elevations so as to create a sloping spillway surface equal to the width of the channel. The second zone is comprised of small boulders, and the third or upstream zone is made of cobble. Photos 5-37 through 5-40. The design is based on the expectation that the large boulders will move, shift, and settle over time as the stream flows across them, and the smaller boulders and cobbles will shift to fill any gaps between the large boulders. Energy is dissipated by the roughness of the cascade as the water tumbles, splashes, and squeezes over, through, and between the boulders. To avoid the risk of the stream opening a channel around the sides of the structure, notches are cut into the banks and filled with large boulders to key the structure into the banks. In sand and silt channels, geotextile fabric should be placed between the footer rocks and the first row of boulders to trap bedload, prevent piping, and reduce settling. Figure 5-23, page 110. The first sheet or panel should underlay the entire structure. A second sheet is installed vertically between the 2 rows of large boulders. No fabric should be placed between the first and second or second and third zones, because this would keep the smaller rocks from shifting and filling any gaps that might develop between the larger boulders. In special situations, filter dams can be installed directly on a bedrock surface where gully erosion has exposed an outcrop. This situation is especially advantageous in that footer rocks are not needed and the structure is inherently more stable. Filter dams are easily built by hand if the bed is armored with bedrock and footer boulders are not needed. Stored water will remain perched on the bedrock for some time, allowing seepage through the dam to enhance the establishment and growth of riparian vegetation. Log and fabric step falls. This structure is used to control head cuts advancing through wet soil areas such as wet meadows, spring seeps, and cienagas. The erosive action can be stopped if a healthy mat of wet soil vegetation can become established to hold the lip of the head wall in place. Photos 5-41, 5-42, 5-43, page 112. Log and fabric stepfalls. This structure is used to control head cuts advancing through wet soil areas such as wet meadows, spring seeps, and cienagas. The erosive action can be stopped if a healthy mat of wet soil vegetation can become established to hold the lip of the head wall in place. Photos 5-41, 5-42, 5-43, page 112. A log and fabric step pool installed in 1993 to control a head cut on Pescara Canyon, Rio Arriba County, New Mexico, was still functioning well 15 years later.
To build a log and fabric structure, Figure 5-24, page 112.
1. Prepare the site by squaring up the head wall, side walls, and bottom of the channel. Eliminate the scour pool and any irregularities, rocks, roots, or indentations in the channel bottom, side walls, or head wall. Use a shovel, spade, pick, or crowbar to shape the sides. Save and stockpile sod clumps of wet soil grasses and sedges for use in steps 3 and 6. 2. When preparation is finished, cut and drape geotextile fabric across the head wall, side walls, and channel bottom. The first should start about 2 feet above the lip of the head wall, extend down the head wall, and cover the channel bottom for 6 to 8 feet, the length of the bottom tier of logs. The second should be draped over one side wall and partway across the channel bottom. The third should be draped over the opposite side wall in a like manner. Temporarily anchor the fabric in place by weighing the ends with rocks or sod clumps. Once logs are placed, the extra flap of material will be folded back over the logs. 3. Install logs in the prepared site using as many tiers as necessary to stack them even with the lip of the head wall. Logs within each tier should be of the same diameter. Logs in the bottom tier should be the longest, the top tier the shortest. For example, if 3 tiers are needed, make the bottom tier 8 feet long, the middle tier 6 feet, and the top tier 4 feet long. It is important to wedge logs tightly against the face of the head wall and side walls. After each tier is complete, use smooth wire and staples to wire the logs together and to adjacent tiers. Fold the extra flap of fabric back over the top of the next to last tier of logs. Lay the top tier on the fabric. Tamp sod clumps into any open spaces between fabric, head wall, and side walls. Note, in streams having bankful depth greater than 1 foot, anchor stakes should be installed. Either cedar posts or T-posts can be used. 4. Working upstream from the lip of the head wall, excavate a smooth platform level with the top tier of installed logs and 1 log diameter wider on either side of the channel. The platform should extend at least 4 feet upstream from the lip of the head wall and have the bottom lined with fabric. 5. Using logs of equal diameter, install the final tier by wedging and tamping each log firmly in place. The logs should be long enough to extend about 2 feet downstream from the lip of the head wall. Wire this tier together and to the rest of the structure. Tuck the upstream flap of fabric in place along the leading edge, upstream face of the logs in the final tier. 6. Transplant live green sod clumps of aquatic grasses, sedges, or rushes to the leading edge and sides of the final tier of logs. Completely fill any cracks or holes between the fabric and channel walls with live sod. This is a key step. The success of the log structure depends on successfully establishing a living mat of wet soil grasses and grass-like plants along the upstream edge and sides of the structure. 7. After installation is complete, return to the site periodically for maintenance. Fill any developing cracks or holes with fresh sod clumps until a healthy mat of vegetation is successfully established and no new cracks or holes develop. Materials needed: geotextile fabric. Silt fencing fabric in 3-foot widths work well and is convenient to use. Logs, 6 to 10 inches in diameter and varying lengths from 4 to 8 feet long. Logs should be straight. They may be green or seasoned, but not rotted. Any protruding knots, limbs, or knobs make stacking very difficult and should be trimmed. Wire, 1 roll of smooth fencing wire. Fencing staples, 2 inches long, about 2 pounds. Sod clumps, 6 inches by 6 inches by 3 inches. Dig locally. Step pools and rock rundowns. One way to repair a high-energy head cut is to lay back the head cut at a less steep gradient and build a series of step pools to gradually dissipate the energy of the falling water. Step pools will tend to maintain the water table within reach of riparian plants, promoting healthy root growth. Low-energy head cuts in small water courses and arroyos can be repaired by laying back the channel at a shallow gradient and building a rock rundown to stabilize the slope, allowing grass plants to colonize the slope. Photo 5-44. For larger, more powerful streams, step pools must be carefully designed and expertly built if they are to meet objectives. Photo 5-45. Several structures of different types applied in sequence are often required to stabilize a head cut. For instance, since head cuts often advance in waves of 3 drops of different heights, a rock rundown might be used to control the upper, more shallow drop, a zuni bowl to control the middle or taller drop, and a 1-rock dam to control the 3rd drop. Adding a 1-rock dam or weir beneath the central structure is always an effective way to reduce the depth of scour while creating a permanent scour pool as a water source for livestock or wildlife. Gully stabilization opportunities. Figure 5-25 on page 114 illustrates a few typical situations where various types of grade control structures, as described in the previous pages, might be used to stabilize an incised channel, arrest further head cutting, preserve a wetland, create a water source for wildlife, or stimulate plant growth, leading to establishment of a new wetland. The pre-treatment schematic depicts, from left to right, a gullied ephemeral channel with an advancing head cut. A head cut rejuvenating a tributary channel that threatens to drain an established wet meadow, opposing large boulders, presenting a suitable site for building a rock arc dam, and a stretch of exposed bedrock where a veneer of sediments might be captured and moisture perched to nurture new wetland vegetation. Exploiting such opportunities for gully stabilization, eventually leading to riparian recovery, will depend on the imagination of the project designer. The post-treatment schematic depicts the outcome of skillful planning, a good knowledge of alternative treatment possibilities, available materials, and a workforce with the tools and experience to get the job done properly. From left to right, one might install a Zuni bowl and one rock dam combination to arrest the head cut and store a bit of water where willows can grow. Maybe a rock rundown is the right approach. A boulder step pool should be considered, especially if the head cut is large and machinery is required for successful treatment. At the tributary channel head cut, a log and fabric head cut control structure might be the perfect answer if there would be sufficient moisture to sustain sod-forming wetland vegetation at the brink of the drop. Farther downstream, the opposing boulders provide an enticing location for building a rock arc dam employing the keystone principle. Such large boulders are suitable for structure anchoring abutments and suggest that plenty of boulders may be nearby for building the rest of the structure. The only challenge now is to gather enough rock to do the job and search for a fitting keystone. Finally, at the downstream site, exposed bedrock has been polished clean of sediment and is bare of vegetation. Is there any hope of recovery? Why, of course. Bedrock is the perfect non-erodible scour-proof footer for anchoring a filter dam, and it is an impermeable base upon which to perch a shallow water table. All that remains is to gather some rock, bring in a backhoe if required, and build the dam. After a few storms, the exposed bedrock will be covered under a veneer of sediment. Water will be detained, soak the sediments, and seep through the filter. A new spring will arise, and sedges will begin to grow, safe from the abrasive wear and tear of abrading gravel. Road crossings at grade control. Road crossings, except bridges, by their very nature automatically establish bed control at the point of crossing. Road crossings include single culverts or multi-culvert arrays, natural or unimproved fords, low water crossings, steel arc culverts, bridges, and porous fill French drain structures. Unimproved fords will tend to either widen or downcut over time, causing resource damage to the stream. Fords, low water crossings, and arc culverts have stable beds composed of native bedload materials. Bridges that span both the channel and the floodplain will tend to remain stable over time, but bridge crossings that span only the channel and not the floodplain will experience concentrated flows that will tend to erode the bed. This tendency can be offset by armoring the channel bed with rocks. Culvert. A simple culvert installation using a corrugated metal pipe is an inexpensive and effective means of establishing grade control in an incised channel and could be an acceptable treatment if adverse effects are properly mitigated. The elevation of the culvert invert, bottom of pipe, sets the bed elevation of the channel upstream of the road crossing. Unfortunately, the use of culverts is problematic in many respects. Culverts can destabilize the channel on the upstream side if the invert is either too high or too low. If too high, sediments will be deposited, causing the channel to agrade. If too low, the culvert will initiate a head cut and degrade the bed. Also, the capacity of the pipe or pipes must be adequate to pass the design flow, or deposition will occur. If flows accelerate through the pipe, then the downstream channel will degrade. A scour pool will result. The bank height ratio will increase. The meander will be truncated, and floodplain access will be diminished. Such effects can be somewhat mitigated by choosing a larger diameter pipe, armoring the outfall to prevent bed scour, and matching the slope of the pipe with the slope of the channel. Culverts can create significant barriers to seasonal movement of fish and aquatic organisms and must comply with state and federal requirements under the Clean Water Act as specified in Nationwide Permit Number 12 that covers soil erosion and sediment control. U.S. Army Corps of Engineers Regulatory Program, http://www.spa.usace.army.mil/default.asp. Multi-stage culvert array. An improvement over the single culvert, a multi-stage culvert array uses a set of 2 or more pipes to establish bed control, accommodating all flows up to the design storm while maintaining floodplain access for flow in excess of bankful discharge. Photo 5-46. The key features of a multi-stage culvert array are that the main tube is sized to accommodate bankful discharge and that the combined capacity of all additional pipes must accommodate the total discharge of the design storm, 25, 50, or 100-year event, that the invert elevation of the main tube be at the elevation of the channel bed, and that auxiliary tubes be at the floodplain elevation. It is necessary to armor the creek downstream of the culverts against scour. The primary benefits in using a multi-stage culvert array are that the floodplain access is maintained at all flow stages. Auxiliary pipes come into play only during flood stage. They tend to remain debris-free and the natural flood regime is sustained. The investment in pipes and embankment materials can be protected by installing an armored spillway at the side of the structure to accommodate any flow in excess of the design storm. This applies to a single culvert as well. Requirements of Nationwide Permit Number 12 with regard to fish and aquatic organisms apply to multi-stage culverts as well as single-stage culvert placements. Having an adequately sized main tube favors fish passage because it decreases velocity. Open bottom culvert. An open bottom culvert spans the bankful width of the channel, maintaining natural channel bed elevation. Photo 5-47. Bed control can be achieved by armoring the bed of the channel under the arc with boulders sized to exceed expected shear forces. – Spaces between the boulders can be chinked with cobble. Bed load movement will restore a natural appearing bed. Passage by migratory fish or aquatic organisms is not obstructed. If properly sized, scour pools do not form. Overbank flows are ideally reconnected to the floodplain by adding auxiliary culverts through the road embankment, as in the example of the multi-stage array. Raised inlets for retrofitting existing culverts. Retrofitting existing culverts to raise the effective invert elevation without replacing the existing installed pipe offers many advantages. Bed control can be achieved without the cost of a new installation. Encased rock berm. An encased rock berm consists of a horseshoe-shaped layer of rock wrapped in a sausage-like casing of geotextile fabric and placed at the upstream end of the culvert. Photo 5-48. Because the structure is porous, any impounded water gradually drains away, maintaining the natural hydro period of the wetland. Zeedyk, 1996. Tie and timber drop inlets. Drop inlet structures can be fashioned of railroad ties and are suitable for shallow to steep gradients and high volume flows. Photo 5-49. When installing drop inlet structures, match the weir edge with the historic meadow surface or the natural channel elevation if the channel is not downcut. Zeedyk, 1996. Porous fill. A porous fill road embankment is used to restore or maintain sheet flow across a slope wetland or cienega which has been incised by road-related impacts. A porous fill is constructed by sandwiching cobble-sized rock, such as screened river rock, between two layers of geotextile fabric. Figure 5-26. The bottom layer of the fabric matches the bed of the channel as the stream seeps through the porous cobble layer. The top layer prevents embankment material from sifting through and plugging the porous fill. If the channel is incised, it is plugged, reshaped, or bypassed, depending on topography of the site. Flood relief culverts can be added on one or both sides to accommodate storm discharge in excess of the limited percolation capacity of the porous fill. For design purposes, a porous fill with 6-inch cobble will pass approximately 1/3 CFS of discharge per square foot of cross-sectional area. This type of structure should only be used on channels with low sediment loads so as not to risk plugging of the interstices between the cobble. Sidebar. Building a porous fill, page 118. Cross vein as low water crossing. A cross vein can be used to stabilize the channel bed elevation at a low water crossing. With the cross vein in place, the stream bed is next armored with cobble and/or gravel-sized material to form the road tread or surface, and the banks are sloped gently back to accommodate vehicle passage. Making the cross vein quite wide with an easily accessible floodplain will help to reduce erosion of the tread materials. Photos 5-50, 5-51. Building a porous fill. Sequential photo documentation of building a porous fill, Colfax County, New Mexico. Photos by Van Clothier. 1. Before installation. 2. Filter fabric laid directly on meadow surface. 3. Porous cobble layer applied. 4. Second layer of filter fabric applied and culvert installed as emergency flood relief with its invert equal in elevation to the surface of this layer. 5. Road bed compacted on top of second layer of filter fabric. 6. Completed permeable fill crossing. 7. Downstream edge showing base flow percolating through permeable cobble layer. Summary. The induced meandering method employs deflectors and weirs. Deflectors are used to influence not only the width of the channel, but also the shape of its banks, the meander length, its sinuosity, and the spacing of pools and riffles. Deflectors include primarily baffles and vanes, which are installed both to initiate lateral erosion of the opposite bank and, just as importantly, to promote commensurate sediment deposition along the adjacent bank. The natural deposition of sediments by size class builds the new stream bank strata, resulting in the formation of an accessible floodplain appropriate to the evolutionary scenario for the expected channel type. The correct sizing and spacing of deflectors is all important to that end. Weirs control bed elevation and control channel grade, and establish the locations of riffles and runs along the channel profile. Structures installed in narrow, steep-sided Rosgen G channels will be subjected to greater shear stress than those structures placed in wider F-type channels. Therefore, size, shape, type of material, and construction technique used during installation will be more critical to their performance in the G than the F channel. When working with water, the devil is in the details. Structures must be carefully designed and properly built to survive and function as planned. How to select, size, locate, and design structures to meet plan objectives is discussed in Chapter 7. Monitoring structure performance to achieve plan objectives and assure timely maintenance and modification of structures is addressed in Chapter 8.